Hey everyone, it's Dr. Pusey. I'm just going to do a bit of a demonstration on relativistic velocity addition. I'm going to start by looking at this scenario here, and it's going to be a classical problem where I've got an observer on the left, which is a stationary child, and on the right hand side I've got another child, but they're on this cart, and this cart is going to be in motion. So what I'm going to do is I'm going to start the problem by making sure that I know what the velocity of this cart or this whole reference frame is going to be. So for this problem, I'm going to set a velocity, and this velocity is going to be written with v, and that's going to be equal to 20 meters a second. Now I'm saying that the left is positive, but you can change it if you like, it doesn't really matter. So this velocity of 20 meters a second is relative to this stationary observer. So that's the first part of the notation of these equations up here, where v is the velocity of the moving reference frame. Now the reason I've chosen the cart instead of the ball's velocity in this case is because there is someone with the cart who's making observations as well. And that's why the first part of any problem, it's best to actually identify what the moving reference frame is. So in this case, someone is on this cart and they are making an observation, and this person over here is stationary, which means this one here would be equal to your v. Now the next object in this scenario is the ball. The ball is being thrown by this kid, and this kid's stationary and they'll be observing it. So this ball will be given the letter U. The question is it going to be U or U dash? Well, it's the same object, but it's just viewed from two different reference frames. So the U without the prime is the velocity of the ball, but notice that it's within the same reference frame as the person who measured this cart. So what that means is it's the velocity of the ball relative to this observer on the left, because this observer on the left is also noticing the velocity of the moving reference frame. If we want the velocity of the ball relative to this child, then what we need to do is U dash, which is the velocity relative to the moving reference frame. So the letter is the same object, it's just the prime or the dash that denotes that it's from a different point of view. So if this observer is throwing a ball, let's just make the problem such that we get the velocity of the ball relative to the observer. So this person on the right, they throw the ball, let's just say they throw the ball at 30 meters a second relative to themselves, right? Now that velocity relative to themselves, it's an observation made by them. So that would be U dash. So U dash is equal to 30 meters a second. I'm making it easy by putting it in the same direction as the cart. And now let's have a look at what the velocity of the ball is relative to this left observer. In other words, let's find out what U is. So we intuitively know that if we have someone on a cart coming towards us and they throw something at us, then those two velocities will be added together. And that's exactly what you see up here in the top corner. So the U is going to be equal to V plus U dash, and we don't have to worry about the correction for a classical case because that denominator just reduces down to 1. So for the simple classical case, and you could have answered this question without doing any maths because I'm sure you knew how to figure it out for yourself, it would have been 50 meters per second. And that's just a relative velocity. So now what I'm going to do is look at the same scenario but using relativistic effects. Okay, so in this fresh problem, we've got a spaceship traveling through a region of space at a velocity of 0.6 c, and they're going towards the Earth. And we have someone aboard the spaceship who's releasing an intergalactic carrier pigeon, right? So they're releasing a projectile, much like that basketball, and it's going in the same direction as the ship's travel, and you've been given a velocity relative to the ship of 0.4 c. And the question's asking for the velocity of the pigeon observed by the Earth. So my way of approaching all of these problems is always to find V first. So in this case, we're looking for something that is moving and also making an observation, and that looks like it will be the ship, and the ship is moving at 0.6 c. Now, because the ship is moving at 0.6 c, its observation of this pigeon will be given as U dash. Now, you are given in the question that the pigeon's velocity is 0.4 c relative to the ship, which means what you have been given is U dash, and in this case I'm making positive to the right. So now that we've worked out what the scenario is actually about, we can just pop it into the equation. Now if we refer back to the classical model that we did above, if I'm moving towards someone at 0.6 c and I throw something at 0.4 c, intuitively we would expect that it's going to travel at 1 c, right? So we've violated the laws of physics right there, because we've just achieved the speed of light. So what we should find is a velocity here that is very fast, very high, higher than 0.6 c, but it should not be the speed of light. So let's just put that in the equation, and it looks like that. And then you just sub in the variables, and notice that these c's cancel out, and then I end up with 1.0 c over 1 plus 0.24. And I put that through, and I get 0.806 c. And that makes sense to me, because I expect this carrier pigeon, according to someone on Earth, it should definitely be traveling towards Earth faster than the spaceship, but it should not be going faster than the speed of light. So I'm pretty happy with that result. Probably be specific and say towards the Earth. What I'll do now is we'll look at an example where we need to use the other equation. Okay, so in this problem, we've got a physics student who's traveling on a train, moving at a constant velocity of 0.5 c towards her school. She's working on homework and she gets frustrated and she throws her pen horizontally towards the wall to make things nice and easy for us. And a teacher at the school makes the observation of the pen to be moving towards them at a reduced velocity of 0.421 c. So the first thing I want to identify is that the train itself, right? The train is moving towards the school at 0.5 c, and that's observed by a stationary observer. So we're going to go ahead and say that's 0.5 c, and that is the moving reference frame, v. Right, now we've got a pen aboard this train, and according to the person at the school, it's moving towards them, and it's moving towards them at a velocity of 0.421 c. So in other words, it's moving towards them at 0.421 c, and that makes it a u, not a u dash. And that's because it's observed by the same person who's observing the train. So according to the person at school, the train's moving at 0.5 c and the pen's moving at 0.421 c. Now intuitively, we would expect that if the pen is moving towards the school at a slower rate than the velocity of the train, then that would mean that the pen must be moving actually relative to the train in the opposite direction. But let's just see if that comes out when we do the calculation. So we now have v and we have u. So the equation we're going to be using is going to be the u dash equation. And notice it's the same procedure where the c's cancel out, but most importantly, this numerator at the top is going to end up being a negative number. So it ends up being a nice round negative 0.100 c. So what does that mean? Well, if I wanted to write that answer better, I would say that means that the velocity of the pen relative to the person who threw it is 0.1 c backwards, or in the opposite direction of motion. And that makes sense to us because the student has essentially thrown it backwards, but it is still ultimately, or relative to the school, traveling towards the school. So this works out quite well with directionality. So there's lots of ways that you can approach these problems, but I think that the quickest way would be to first identify the moving reference frame and then look at your object and ask yourself, well, is the question giving me the velocity of the object relative to the stationary observer, or is it giving it to me relative to the moving reference frame? And then once you've been able to identify that, it really is just a matter of just plugging it into the equation and making sure that you don't get a number that's greater than the speed of light and that the number you get is something that you might expect. So I hope you find that helpful.